everybody. In the last class, we discussed static 1 hazard. We saw that an otherwise optimized circuit can create issues in terms of producing glitches, which could be troublesome in some of the applications. And in that context, we found that how to detect such hazard for certain kind of circuits, and that is static 1 hazard, and how to cover it. So, in today's class we shall look at static 0 hazard and dynamic hazard. So, these are the two things that we shall take up today. So, in static 0 hazard we shall again the condition that we find is similar, is analogous to what was there for static 1 hazard. In static 1 hazard, if we remember, the Boolean expression reduced to something like a plus a prime equal to 1. Just to recollect, the Boolean expression reduced to a plus a prime equal to 1, which always needed to be at 1, but because of the propagation delay involved in generating a prime through an inverter, we found a negative going pulse or a glitch occurring, and we found how to detect that and how to cover that. So, in static 0 hazard, what is happening, the Boolean expression for a certain combinations of the input reduces to an expression which is something like a prime, which should generate 0 as far as the logic of the circuit is concerned, but because of the involvement of these time delay, finite propagation delay in generating the NOT gate output, there is a glitch. Okay. So, this glitch will be a positive going pulse. Okay. So, how does it occur? So, if you look at the example, so this the input A is going from changing from 0 to 1, okay. And because of the input is going from 0 to 1, A bar is going from 1 to 0, but it takes a propagation delay, which is propagation delay for this inverter, this NOT gate going from high to low. Whatever time it requires, the finite propagation delay associated with this circuit, whether it is a TTL based circuit or a CMOS based circuit, there is the that delay associated is actually included in this duration, time duration, that tau 1 you see. Okay. So, for this AND gate, this particular time duration, this 0 to tau 1, that one you see over here, is the time when both the inputs are at logic high, logic 1, right. So, because of which whenever they are at 1, both of them are at 1, after the propagation delay involved for the NAND, this particular AND gate to go to logic high. So, it will go to high, and whenever it goes to low, it will go to low. So, during that period it remains high. So, this is this positive going pulse that you see for a short duration because of the propagation delay involved here. Okay. So, but for the AND gate, you know, I mean AND relation, for this kind of relation you should always get a 0, which is not happening because of the finite propagation delay. So, in static 0 hazard, output should always remain static at 0 according to the Boolean logic, but glitch occurs because under certain input condition. So, we look at one practical example. So, if you realize the truth table that we had seen before for the static 1 hazard problem, the same truth table if you try to realize through product of some POS, then what we get? We will get a relationship something like this. So, this is a known problem, this relationship we have seen earlier in the course, okay. And to realize that, we are having A or C generated here and A prime B generated over here, and these two are ANDed through this AND gate. Okay. Now, consider the input combination B is equal to 0. So, this is 0, C is equal to 0. So, this is 0, okay. And A is going from 0 to 1. So, A initial is at 0, right. So, which is making initially this is at 1. Okay. So, 0 and this is at 1. So, this output is 0, right. This output is 1, but for the AND gate we need both the output to be 1 to be out for the output to be 0. Now, this goes from 0 to 1. Okay. So, this AND gate after the OR gate after the propagation delay goes to 1, but this one till this time this NOT gate output changes will remain at 1. Okay. So, this output 1 goes to 0 after this propagation delay and this propagation delay. Okay. So, because of which here it goes to 1 after 1 propagation delay and it goes to 1 after 2 propagation delay if tau 1 and tau 2 are same. So, momentarily for 1 propagation delay both the inputs are at high, okay, which makes the output high. So, because of which this glitch, the one that we are talking about, occurs in this circuit. Okay. So, for other input combinations it will not occur. So, that is what it is mentioned in the earlier class also, and that we take note of here, that for a specific condition combination these thing the glitch occurs. Now, how we detect static 0 hazard? So, static 0 hazard detection is similar to static 1 hazard detection. Okay. So, two logically adjacent cells with output 0 in the K map, if it is not covered by common sum term. Okay. In static 1 hazard it was two logically adjacent cell with output 1 not covered by common product term. Okay. So, in this case it is the output having 0 which goes into the making of POS expression, they are not covered by common sum term. So, from the Karnaugh map we can find this one, and if you look at the Boolean expression which ultimately reduces to a prime kind of thing, a variable and its complement ANDed together for certain input combination. Okay. So, we do not need to go up to the expression level, simply by looking at the Karnaugh map grouping from which the expressions are generated, we can detect presence of a static 0 hazard. So, we look at one example. So, this is an example where you see the these zeros, this is the optimized expression, right. So, these two zeros and these two zeros, they are grouped together, and a plus b prime is one term, this term, and b plus c is the other term, and they are ANDed together. Okay. So, there is a potential glitch, static 0 hazard. Why? Because this 0 and this 0, they are logically adjacent, okay, and they are not covered by one common sum term. Is it clear? So, when does the glitch occurs? When a is equal to 0 and c is equal to 0, a is equal to 0, c is equal to 0. So, this is the two cases, when a is equal to 0 and c is equal to 0 and b changes from 0 to 1, then the glitch occurs. Okay. Going by whatever we had just discussed the example. So, similar example over here. Now, if you look at the other truth table, a similar truth table in relation to what we discussed in the static 1 hazard. So, there we grouped the ones, now we are grouping the zeros. So, this is one group and this is one group, and they are generating term b plus c and b prime plus c prime, and we are ANDing them together, okay, to get the POS representation. Now, we see that the logically adjacent zeros, these two, they are under common sum term. These are two logically adjacent zeros, they are under common sum term, and these zeros are not logically adjacent. So, they need not be covered by common sum term. Okay. So, we do not have any hazard here, we do not have any static 0 hazard here. Okay. So, that is what we take from this particular truth map table and convert it to Karnaugh map. Okay. Now, we look at a 4 variable example. So, this particular example, you see the presence of zeros and ones in that truth table UA, it has been mentioned, and to get the first the optimized expression. So, we look for grouping of zeros with largest possible group size. So, this is one group, this is one group, right, which is generating this term a plus C, right. Then we have this particular group, all 4 zeros they can be grouped together, right. So, this is generating C plus D prime, and the other 2 zeros, these 2 zeros and these 2 zeros, they can be part of one group, okay, group of 4 members. So, that is between them 0 0. So, B plus C is remaining with 1. So, C prime. So, this is the third term that we are getting, which is covering all the zeros, right. So, this is the optimized expression, but does it have a static 0 hazard? So, for that what we need to examine? We need to see whether the logically adjacent zeros are covered by common sum terms or not. These are logically adjacent zeros covered by common sum term, but here is one logically adjacent 0, okay, I mean zeros, one pair, they are not covered by common sum term. Okay. So, this might lead to a glitch for a specific input combination, right. So, is there only one possible way the glitch can occur? No. You can see that there is another such thing, okay, which is they are logically adjacent, and but they are not covered by common sum term. Is that the only second only possible thing? There are no other ways glitch can occur in this particular example. There is another way glitch may occur if you look at this 0 and this 0. Okay, they are also logically adjacent. So, and there is no common sum term covering them. Okay. So, there can be a glitch for that also, right. So, what are these possibilities, the combinations? So, between these two you can see A, B and A, B remaining 0, D remaining 1 and C changing from 0 to 1. So, A remaining 0, B remaining 0, D remaining 1 and C changing from 0 to 1. So, A 0, B 0, D 1, C changing from 0 to 1. Okay. So, this is a case where A, B, D are 0, 0, 1, C changing from 0 to 1, a glitch, a negative, a positive going false will occur when it was logically it is supposed to be at logic 0. If you look at the expression, if you substitute, we can see that the same thing will be happening. So, A is equal to 0. So, this is 0, right. Then B is equal to 0, B is equal to 0, this is 0 and D is equal to 1, right. So, D is equal to 1 means D prime is 0, right. So, what we will get? C and C and C prime. So, C prime is occurring, right, a variable and its complement. So, this is a case where there is a possible glitch, okay. A glitch will occur if we make a transition, if the input C make a transition from 0 to 1. Similarly, you can check for the other cases also, right. So, this is the case when 1 A is 1, right, B is 0, right, and D is 1, D is 1 between these two, right. So, A 1, B 0 and D is 1 and C is changing a transition from 0 to 1, okay. Glitch occurs. And the last one, the third one that we talked about, these two. So, A is 0, B is 0, D is also 0, right, between these two zeros and C changes from 0 to 1, C changes from 0 to 1, okay. So, there is a glitch occurring, right. So, this is the way we can figure out 3 such possible glitches and this particular realization has a has static 0 hazard. Okay. Now, to cover, we have detected, but we need to think of how to cover it, and again we follow the logic that we followed for static 1 hazard covering. So, the one that causes the specific hazard, we need to make sure that that cause does not arise. So, for that what we will do, simply we shall see that the adjacent logically adjacent zeros are covered by one common sum term. So, in the previous example, in this particular example, right, what we are looking at this two zeros, right, we are covering by a common sum term. Okay. So, this is the example with which actually we started. So, this particular circuit is of this is one sum term a plus c, right, a plus c, okay, and this is another sum term which is a prime plus b, a plus c and a prime plus b, right. So, this is the one with which we started today's discussion, right. So, if we quickly go back, so this is the circuit we started with, right, and we found that there is a possibility of a glitch. So, we are looking at covering this particular hazard. Okay. So, these are the two terms, right, and then the common term over here is b and c. So, we are forming a group of them. So, a group of it. So, b plus c. So, when we are just forming this term, this is so called redundant term in terms of optimization problem, but together it solves the problem. I mean, the addresses the static 0 hazard. And how does the circuit changes? So, basically this is the b plus c that comes over here, and when b and c are 0, these two are 0, this output is 0, and this holds, this is the AND gate input. So, if there is a 0, it will be always a 0, right, and even if some changes are occurring over here, a going from 0 to 1, that is not going to the final output. Okay. So, this is similar to what we had seen in case of static 1 hazard, a third AND gate was there which was feeding to the final OR gate. Okay. So, a just analogous thing in terms of POS representation. Is it clear? So, now we look at the other example, the 4 variable example, and there are 3 glitches, 3 possible glitches that were to be covered, and so in this case what we are finding, we find that to cover this one and this one, I mean these two zeros, we can form a larger group, isn't it? We can form a larger group, I mean the group of 0, otherwise you could have one term over here, another term, one common sum term, right. So, then we would have required 2 such terms with 3 literals. So, but we know that we can have a larger group of 4, which will make sure that all adjacent zeros like these 2 and these 2 are under one common sum term. And for that what we are having? So, in this b is remaining constant and d is remaining constant, b is remaining constant with 0 and d is remaining constant with 1. So, b plus d prime is the term that will be required. Okay. And the other thing is this 0 and this 0 that were to be put under one common sum term. Okay. So, one option is to have like this, but again that will require 3 literals, literal cost would increase, and what we would like to do to avoid that, we will be having a larger group like this with only 2 variable involved. So, that is a plus b, because a b is remaining constant over 4 zeros. Okay. So, with all of them together we can see that the static 0 hazard for this circuit, all the 3 possible cases are covered. Okay. Right. So far we had seen the static 1 hazard and static 0 hazard using AND OR and OR AND kind of 2 level circuit. We are only talking about 2 level circuit here, as we have noted before. So, if we had used instead NAND or NOR for realization of this 2 level circuit, okay, what would have been the case? Okay. We may have certain curiosity about it. So, let us look at one quick example. So, if this is a realization of A prime C plus A B. Okay. So, this 2 level realization in this case is achieved by using only NAND gates. Okay. So, these are the 2 NAND gates, and finally, this is the third NAND gate, which is just combining the output of the previous 2 NAND gates. Okay. So, this is we are familiar with from our week 2 discussions, how we are getting this kind of circuits. We can use De Morgan's theorem also on AND OR, and then we can get an AND kind of circuit. Okay. So, in this case what happens? So, we had seen before. So, we continue from there that A bar plus A, this comes when B and C are 1, is not it? B and C are 1, A and A bar plus A bar kind of relationship is coming. So, that is has a potential glitch, and when A goes from 1 to 0, right, that is the static the glitch will occur, right. So, so what is happening over here? This is NAND. Earlier we had studied AND OR. So, in this case initially let us consider all this situation, B is 1, C is 1 and A is at 1. Okay. So, A is at 1 means this NAND gate NOT gate output is 0, which is fine. So, what are the corresponding NAND gate outputs? So, this is 0, 1 1, this is 0 and this is 0 and 1. NAND gate 0 is the forcing input. So, this the output is 1. Okay. So, 0 and 1 output is 1, which is fine. Now, this is the thing that you see that at this point of time, NAND gate is making this input A is making a transition A to 1 to 0, right. So, this has become 0 after one delay, it will become 1, right. So, but here this 0 to 1, this 0 to 1 that you can see goes after one propagation delay over here. So, it will not, when it is becoming 1, it is not immediately going to 0, because input 2 is fed is delayed. I mean the input of 1 is delayed by the propagation delay of the NOT gate. So, for one such delay period of this NOT gate, both of them are 1, both this one is 1, this one is also 1. So, this 1 will make the output 0 for that amount of time, including involving all the propagation delay of this gate and this gate, right. So, that is the glitch we are talking about. So, the similar glitch occurs, the one kind of thing that we had seen for that relation, it is occurring over here also. Okay. So, how to cover it? So, to cover, so this B and B C will be the one that we had seen, we earlier this is the one that we had considered one AND gate, and it was going to the third input of the OR gate. Similarly, it will be B C NAND, one NAND gate will be there with B and C, right, and this will go as the third input over here. Okay. Similarly, for POS realization, right, if we go for NOR, right, we shall have B is equal to 0, C is equal to 0. This is the snapshot of the different logic values. Then A goes from 0 to 1. Okay. So, A goes from 0 to 1 over here, and then A bar goes from 1 to 0 like this with this propagation delay. So, momentarily both of them are having, so this is having 1, sorry, and this is also having 1, right. So, for a NOR gate 1 is the forcing input. So, this is 0, at that time this is also 0. So, 0 0 the output is becoming 1. Okay. So, this is something that we take note of, that whether you realize by NAND or NOR or the corresponding AND or AND, the result remains the same and the covering is similar. Okay. And one might note that if we can introduce in this path a delay which is similar to this delay, then this can be avoided. Similarly, if we can add a buffer which is providing this amount of delay, okay, but that is we need to be careful that this delay is added in appropriate amount, otherwise it will not help the situation. So, better to cover in this manner, but by adding delays also you can avoid it. Okay. So, dynamic hazard we shall discuss now. So, dynamic hazard is a case when there is a potential for multiple transitions. Okay. While the circuit is required to make one transition from 0 to 1 or 1 to 0, but it is making more than one transition. So, this is what is known as dynamic hazard. So, basically the changes the way we have seen in the right hand side. So, this kind of changes take place, and for this one we would notice that one of the input variable which is actually causing this thing is to have 3 or more paths to the output and number of levels involved. Earlier we saw that there are 2 levels. So, number of levels should be 3 or more. Okay. And inherently one can see the relationship like what you see over here, a plus a prime and a, or a plus a prime and a, this kind of thing. So, inherently there is a static 1 and static 0 kind of relationship emerging somewhere, and this is what is visible in a dynamic hazard causing circuit. Okay. So, we will look at one example. There is a example where you can see this is AC plus BC prime, right, ANDed with CD prime, and we are looking at a situation when A is equal to 1, B is equal to 1 and D is equal to 1. So, potential you can see C plus C prime and C prime, this kind of situation emerging. Okay. So, this is just example. So, what happens at that time you can see from this particular diagram. So, this is the value of the other inputs, okay, and C is making a change. These are the outputs y1, y2, y3, y4 and y, intermediate outputs, okay, for the purpose of plotting. So, C makes a change, makes a transition from 1 to 0, right, and then because of that y1 will go from 0 to 1 because D is held at 1, right. So, then it will go to 1 after 1 propagation delay, fine. What happens to y2? y2 is a AND gate, right. So, if input changes from 1 to 0, so the output will become also 0 because C was 1, C was held at 1. So, output was 1 because of presence of A as 1. So, because of which this y2 is also becoming 0 after 1 propagation delay. We are considering same logic family, more or less same propagation delay tau. Okay. After that it remains same at that value. What happens to y3? y3 is AND of B which is 1 and AND of y1. So, both of them when it is 1, the output will become 1. So, both of them are 1. So, this is y1 is 1 input, right, and B is already 1. So, it goes to 1 over here. So, it will take time, 1 propagation delay for this AND gate, right, for which y3 becomes 1 over here. Now, what happens to y4? So, y4 is OR of y2 and y3, right, any one of them high, output will be high, that is the idea. So, this is the y4 we are talking about. So, this y4 if you look at, we need to look at y2 and y3, right. When any one of them is 1, the output will be 1. So, you see that y2 is 1 here, this is low, but y2 is becoming low in this place. So, after 1 propagation delay this will become low, right, and y3 is going high here in this place. So, after 1 propagation delay this will become high, right. Finally, y4 and y1 ANDed together is the y, right. So, this is y4 and y1. Okay. So, this is the y1, both of them need to be high. So, y4 was 1, right. So, this one making it high after 1 propagation delay, right, both of them need to be high y4, right. So, after that this y4 has gone low here. So, that is making low in this place, right. Then y 4 goes high. So, this is going high. Okay. So, then what you see, the y is like this, and if you look at the corresponding logic here, C plus C prime and C prime. So, basically it is C C prime plus C prime. So, C prime only. So, when C changes from 1 to 0, output should go from 0 to 1, but here output is going from 0 to 1, then again coming to 0 and then again going to 1. So, instead of one transition, it is making multiple transition. So, this is what is seen as dynamic hazard, and how to cover it? It is relatively more difficult than static 0 and static 1 hazard. To see what is this inherent static 1 hazard can be seen over here because of the C plus C prime kind of relationship, and to cover it, we will be having, it is happening for A is equal to 1, B is equal to 1 case, which you have seen investigated before. So, you add one additional term, right, A B, without making any difference in the truth table as such. This is the redundant term. So, that will be coming in parallel to this as A B, A and B, right, and that will be getting connected over here, right. And after that, you will be seeing that when your A, B and D is equal to 1, right. So, this is at 1, A B is held at 1. So, 1 and C D prime. So, basically 1 and C prime, that is what we will get, or C prime. Okay. So, only one transition will take place. So, with this we end today's discussion very quickly, summarizing what we discussed today. Static 0 hazard, output should remain static at 0, but glitch occurs for certain input combination. Static 0 hazard can be detected by examining the Karnaugh map and the Boolean expression. It can be avoided also by including additional sound terms and appropriate delay, that we have noted. In dynamic hazard, potential for multiple transition exists, and instead of only one, which is required from the logic relation, and it requires 3 or more level of circuit, and the inherent implicit static 1, static 0 hazard, if identification of that and covering can avoid its occurrence. Thank you.